Newton's universal law of gravitation. Here is the equation. The force of gravity is equal to the product of the two masses that are interacting divided by their center-to-center distance squared multiplied by the universal gravitation constant, G. So there is a force of gravity, a force of attraction, gravitational attraction between any two masses. And it's given by this expression. Now, the gravitation constant was determined in 1798 by Henry Cavendish. And it was found to be equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So let's take a look at an example. Suppose we have two 1 kilogram masses and we place them 1 meter apart in space. And we wish to determine the gravitational force of attraction between the two masses at the beginning, right here, before they start to actually move. So, using Newton's universal law of gravitation, we have that Fg, let's go to capital G. We have the two masses, and we have the center-to-center distance. So we take 6.67 times 10 to the negative 11 unit Newton meters squared per kilogram squared. M1 is 1 kilogram. M2 is 1 kilogram. All divided by 1 meter squared. So you can see that the gravitational force between two 1 kilogram masses that are 1 meter apart is initially 6.67 times 10 to the negative 11th newtons, a very small number indeed. Let's take a look at another example. Suppose we have a very, very, very tall ladder. We set it up so that someone can climb as high as they want above the surface of the earth. And let's say at the surface of the earth, the person has a weight W. Well, what is the distance that that person is away from the earth? Well, we would say the radius of the earth, because the distance that we use in Newton's universal law of gravitation is the center-to-center distance. So now suppose the person climbs up the ladder so that he's at a distance of 1 Earth radius from the surface of the Earth. Well, when we use Newton's universal law of gravitation, we can see that his distance to the center of the Earth is 2 times the radius of the Earth. So the gravitational force he experiences here, which we call his weight, would be equal to this represents his mass. This is the mass of the Earth. Now we're going to divide that by 2 Earth radii, and we square that. So we get G, M, ME all over 4 RE squared. Well, isn't that 1/4 his weight at the surface? Because his weight at the surface would be given by Fg is equal to G, M, ME over RE squared. So this here, his weight here would be 1/4 what it was here. If he climbs an additional radius of the Earth, his weight would be 1/9. Now let's do something else here. Suppose we wish to determine what the acceleration due to gravity depends on near the surface of the earth. So we're going to imagine this person dropping a rock. Okay, so he's holding a rock and he's going to drop it. Well, as the rock is falling, the net force on it is the weight of the rock, which is equal to the mass of the rock times the acceleration due to gravity, which we're investigating. Using Newton's universal law of gravitation, we can say that the gravitational force on the rock, which is the weight, or mg, is equal to the universal gravitation constant times the mass of the rock times the mass of the earth divided by the center-to-center distance, which is the radius of the earth, squared. Notice that the mass of the rock cancels out, so we can see that the acceleration due to gravity is not dependent upon the mass that is falling. It's only dependent upon the mass of the earth and the center-to-center distance between the falling object and the earth squared. And of course, that universal gravitation constant is inserted there. Pretty cool. Now, this is the equation that was used in around 1798 to determine the mass of the earth. Because you see, let's say we don't know the mass of the earth, but we know g, this value, and we know this value here, right? This is the free fall acceleration, which was measured, could have been measured easily in 1798. This was known in 1798, the universal gravitation constant, and the radius of the earth was known for thousands of years prior to 1798. So if we solve this equation for the mass of the earth, we get g, the acceleration due to gravity, times the radius of the earth squared, divided by the universal gravitation constant. And if we put the numbers in, we get the mass of the earth, which is about 6 times 10 to the 24th kilograms.